Hey physics student, Mr. Argentas here. This is chapter 7. We're talking about circular motion and centripetal acceleration. Now, one thing about uniform circular motion is that it has constant speed in a circular path. Now this sounds very confusing. We have constant speed and acceleration at the exact same time. How can it possibly be that those two ideas don't go together very well at all? The reason why we can have constant speed and acceleration at the exact same time is because the direction is changing all the time. Therefore we have acceleration. So centripetal acceleration, what we're going to do, we're going to call centripetal acceleration A sub c. Centripetal acceleration, we're going to find it using the velocity vectors, because if you remember that we found acceleration to be the change, the resultant vector as the change in final velocity versus initial velocity. So here's initial velocity, here's final velocity, and as you can see, it's tangential to the circle. We know this because as soon as the force drawing it to the center of the circle is released, it goes straight. We've all experienced that. But if I just draw this, vector, this velocity final vector again right here, here's my velocity final vector, and I go back to what I said a minute ago, that the change in velocity is velocity final minus velocity initial, and I took the velocity final plus the negative of velocity initial, which is the exact same thing. The negative of velocity initial would just be this one flipped upside down. Well, if I flip that one upside down, then the resultant vector would be the resultant vector is acceleration, and that resultant vector is pointing directly towards the center of the circle. So here's acceleration, and we're talking about a centripetal acceleration. And so this is the negative of velocity initial, is what that is. All right? And so this is just sort of a proof that the centripetal means center-seeking acceleration is pointing towards the center of the circle. So the direction of the acceleration is towards the center of the circle, and that's called centripetal. By definition, that's what centripetal means, center-seeking. Now, the equation for acceleration, centripetal acceleration, is velocity squared over radius. So v squared is velocity, r is radius, and a sub c is, as I already said, is centripetal acceleration. Right. So let's take a look at a question. A car travels clockwise at a constant horizontal circle which arrow indicates the direction of the centripetal acceleration. Well, here's our circle. Here's A, and this is B, this is C, and this is D. So would this be the acceleration? Would this vector be the acceleration, this one, or A? certainly it would be A, because as I just showed you, the centripetal acceleration by definition is center seeking, towards the center of the circle. Another quick question: which graph best represents the relationship between the magnitude of the centripetal acceleration and the speed of the object moving in a circle? Well, here's speed down here on the x-axis, and on the y-axis, centripetal acceleration. Well, we have a direct relationship here. We have a direct relationship here. As one goes up, so does the other. And then we have a relationship here that appears to be the inverse square, and then this is an x squared. This would be the best, because this is if I remember my geometry, this is an inverse square, and then this is x squared, because it rapidly increases. And the reason why I use that, if we go back to our equation, A sub c equals velocity squared over r. And so, which represents the magnitude of centripetal acceleration and speed? Well, it's the speed is squared, so that's why we would have to use this graph best represents that square relationship. All right, and then this is a problem in your book. This is practice A, page 236. I just rewrote the question. A rope attached to a tire swing has a centripetal acceleration of 3 meters per second squared. That should be superscripted. The length of the rope is 2.1 meters. What is the speed, the tangential speed? Well, here's our circle, and if you could picture, there's the tire swing here. Here's our radius, and that's given to us. We know the radius is 2.1 meters. That's good. What else do we know? We know that the acceleration is 3.0 meters per second squared. Right. So we know the acceleration. So we can just refer back to our equation. A sub c equals velocity squared over radius. Now, when you look at this, the first thing you should be thinking is how are you going to get what you want? Because in this situation, we have AC and we have R. We want V squared. So AC RV squared. If you want R, you would divide these two. If you want AC, you would divide these two. And if you want V, you multiply these two. All right. So that's what you remember from you remember setting up that triangle whenever you did density. It was the exact same relationships. So what we're going to have to do is 3.0 meters per second equals velocity squared times 2.1 meters. And we want to solve for V squared, so it's just going to be 3.0 times 2.1 equals V squared. And get rid of that, we'll just put it on radical, and then so it would be 2.5 meters per second would be our velocity. All right. Now, also there's centripetal. There's also there's centripetal force. The centripetal force is mass times acceleration of the centripetal acceleration, which is something that we need to address next.